Today we're going to get an up-and-close personal look at one of the coolest robots I've seen at the FTC World Championships.
Each turret moves on an axis.
This is Team 15991 Gamma from Romania, and this was at the FTC Decode 25-26 World Championships.
Wow.
They've got a lot of really slick packaging mechanisms here with a triple turret.
Shooting time, for now, it's 0. So you launch 3 artifacts.
A flywheel system where the motor integrates inside of the flywheel itself.
Each turret has an integrated motor inside the flywheel,
as well as some really slick linkages used to make sure they don't intake too many game elements and make sure the game elements always index to be exactly the way that they need to be.
Hey, so tell me about your overall robot. What do we have in general going on here?
So it's triple turret design. Very important to notice, not the triple shooter, a triple turret, because each turret moves on an axis. It's the smallest design that's possible with a triple turret. So the turrets are actually very small. Each is included in a virtual 210 millimeter circle so that they can spin without touching each other. Each turret has an integrated motor inside the flywheel. That way, with direct drive, we get the most compact design possible for a turret, and also a very quiet one.
So it's literally sitting inside.
Exactly, yeah.
Of the flywheel. Oh, that is super slick.
Then each turret has its own Axon Max servo motor that controls the hood separately, so that in the match, we calculate the distance between every turret and the goal. And each hood has a different angle.
And the hood is changed on a saying with just this little 2-bar linkage.
Yeah, 2-bar linkage.
Right inside there. It's on both sides.
Exactly, yeah. To be able to lift the hoods equally.
Mm-hmm. And you just got a straight axle that enters through. A question on your flywheel.
Sure.
How is the motor actually charging on the inside there? Do you have a large round gear, like a planetary gear on the inside?
No, it's just simple motor with no gears. So this is a big bearing, and this comes on top of it. It's actually a 3D printed piece with custom silicone poured into it. Then when the silicone hardens, it becomes a part of the plastic component that just gets slid onto the motor, and it becomes one piece.
Oh, that's super slick. I love that packaging design. That's awesome.
Yeah, we needed to do that because if we hadn't got small turrets, our design would be impossible. Then the 2 front turrets each have manual targeting system. It's composed of one rev color sensor that has an LED. The LED shines a light to 2 dental lenses, like the dental glasses. And then the light gets collimated and focused to not a point, but the rays go parallel. So that, let me explain into depth. The localization on the robot is on pinpoint, but due to vibration of the flywheels, it causes drift over time. So when we see drift, we turn on the limelight, relocalize on the limelight, then go back to the localization on pinpoint and shut off the camera. But to detect that drift, I'm driver 2, so I control the systems of the robot. I look where these 2 points from the LEDs are actually on the goal. And if I see that they're off, I just turn the camera on, reset, shut the camera off, and then the localization goes back to pinpoint.
That's super slick. I love having manual overrides for things, or in case something's going wrong.
It was mainly used for our league meets where we had a problem with our pinpoint that scared us a bit, and then we came up with this design. So now we're going to reset the robot on a QR code to be able to see the actual tracking. In the interior of the robot, there is actually a linkage system. When we hadn't implemented it yet, the robot could easily intake 5 artifacts. So now we put in this linkage that limits the space on the robot to 3 artifacts.
So how does this little linkage work then? It makes basically you have a large front section that's able to take in a lot of artifacts. And you've got this, I don't want to touch it because now it's powered. I don't want my finger to get stuff. And that's able to move it out so you can reduce the amount of space you have.
Exactly,
because it's a huge internal capacity, right?
Yeah.
Yeah.
If you put artifacts by hand, it can intake about 13.
You actually have built a robot that's functional in the FRC season.
Exactly, yeah.
Season. Yeah.
Many people said that.
That's awesome. And then how does the ball, so once you get it inside, you've got a straight bar here. How does the ball, once it's inside, actually get up and into the flywheels?
So usually the driver intakes by linkage. So you have the linkage active.
Yep.
3 artifacts get in line. And then because it's impossible for them to stay straight, the back one gets like this position. And then the 2 front ones aren't exactly placed in a line. So they go left, right, or vice versa.
Yeah.
So then after that, we have lock sequence. The linkage goes into the robot. Then you see the little elevators have some kind of steps. So it's not just a straight movement from down to up. It's something on 3 locks. We call it lock 1, lock 3, and lock 2 and lock 3. These assure that the artifacts don't jam inside the robot and actually get placed just under the flywheel, where a color sensor reads their color. Then, so if we want to sort, we have the fastest sorting capability.
You actually don't know what color is until it's at that second stage before it gets fed through into the flywheel.
Yeah.
Okay.
So then for color sorting, something that we found out, it's a bit of a detail, but it's still interesting. The color sensors actually take up quite a lot of processing power, and them scanning the entire match isn't really optimal.
Yes.
So we have a button that actually shuts off the reading of the color sensors.
Okay.
So that in the match, we just play normal. Like we intake 3 artifacts, shoot them one at a time. No, sorry, not one at a time, just sorting.
Yes.
We shoot them 3 at a time, simultaneously. And then
because it's on the I2C port, and the I2C port is quite slow because you can't bulk read over I2C.
Yeah.
Yes.
And then just at the end of the match, we start the color sensors, read the colors, and sort if needed.
Oh, interesting. Yeah, because color doesn't matter.
Exactly.
Oh, that's fantastic. I love that.
So we have our code running very smooth.
Super creative. Super creative. Now, a question I have is, once you've got artifacts inside of the robot, how do you know when you have 3?
So at the end of the season, our color sensors that can act as distance sensors as well were placed down here next to each elevator. Out of the start of the season. Sorry, so that it would automatically go into the 3rd stage when it had 3 artifacts. But we found out that that was kind of a slow process. So we just switched to manual. That's driver practice.
Yeah.
So when you have 3 artifacts in the robot, the chassis driver just backs out of the artifact pool, and the second driver activates the lock sequence.
Okay, so you've just had lots of practice. You've got lots of open space on the robot.
Exactly.
So it's pretty easy to see the inside of your robot.
Yeah.
And that's good enough to know when you've got 3 inside.
That's why we actually not only pocketed the metal parts of the robot, we pocketed also we call it tab of the robot because it's white and quite wide. So we have lots of holes in that, so we can actually
really easily see.
Yeah,
really easily see. Very good.
For the bearings of the turret, it was quite a challenge. So, avem de plastic? Let me just get the 3 bearings.
Yep.
At the start of the season, we tested it with plastic bearings. The off-the-shelf bearings are very heavy, and with the triple turret, that's the main concern of the robot. Now it has about 16.12, like
16.2 kilos. Yeah, that's pretty heavy.
So that's pretty heavy. We started with these plastic bearings. They were okay, but not great for accuracy. So our first aluminum attempt, these aluminum custom bearings that have a V-groove on them. Actually, this V-groove was doing well, but the V-groove bearings that were found on GoBuilder, actually, they're sold as V-groove perfect 90 degrees, but in the real world, now nothing is 90 degrees. So we added slant on the actual bearings. So they're cut 90 degrees. Then the corner is actually reduced a bit. so that the bearings run off not on the interior edge, but on the sides.
Yes.
So that we get very, very good accuracy on the actual turret.
Okay. So you've got a V-groove bearing sitting on the inside. And if I'm correct on that, that's what these little guys mounted here are. You can see them just very narrowly snaked inside there.
These screws are custom made. So if you look closely to them, you'll see that the hex is not really it's not perfectly on center.
Yeah.
Like it would be on a store-bought screw.
Yep.
The normal screws aren't exactly 4 millimeters in diameter. And to have that accuracy, we want it exactly 4 meters in diameter.
Yep.
Not with a fillet on them,
yeah.
but just plain.
Yes.
Yeah, you can see here.
Okay, yes. So you're exactly on 4.
Yeah,
so interestingly enough, on a sidebar there's a manufacturer out of Japan called Misumi that makes the same there that isn't exactly a 4 mil with the small side.
Yeah.
Really cool that you make it manually.
We custom made them to be sure that there are exact dimensions.
Yeah.
So the exact length, the exact width, the exact everything.
Super cool. And then you have a CNC shop to be able to do that.
One of our sponsors, actually, Vesta, that in Romania makes all of the road markings, the traffic signs, has CNC workshop, not a CNC, but lathes, and then laser cutting. So we first laser cut the parts and then put them on a lathe. Well, we had teams, firstly in the summer, we iterated on a lot of chassis. So our final iteration got about 550 RPMs.
Okay.
Some would say that that's a bit too high, even for a small chassis.
And for a heavy chassis too.
And for a heavy chassis, and that's the fun part. We actually used the same RPM on the chassis as the test rig in summer.
Okay.
So the robot gets 550 RPMs.
Okay.
We had people tell us that it's quite a high RPM and we could actually get more speed if we lowered the RPM to increase the torque. But actual tests, weirdly enough, showed that that's not true. So a robot is actually built on the limit of the part. So after some 20 minutes of driver practice, the drive motors are very hot.
Yeah.
But if we decrease the gear ratio, the robot would have run slower.
So you just make sure you cool them down or add an aluminum heat sink or something like that.
For us, because the whole robot is actually made of aluminum, the plates that hold the motors actually act as heat sinks. And then because the plates are bound to the actual chassis with aluminum parts, the heat is actually very well transferred.
So you're using a 435 RPM, or what RPM is this? And then you have a gear
This is
reduction as well.
1,150.
Okay. Yep.
And then approximately 2 to 1. Then that goes to the direct economy.
Yeah, and then you're using the 30A from Go Build on that.
Yeah. So at the start of the season, we actually used normal Grifols parts. But for the championship, we switched to 30A.
And what are you guys most proud of on this robot? Obviously, the triple turret, I would imagine. Yeah.
We're proud because it works very good. At our championship in Romania, it performed very well, exceptionally, I would say. And we're still able to develop lots on it. Single turret, being more simple, has kind of like a bottleneck for development. It's a single turret, you perfect the turret, and then that's that. Because we have a triple turret, we can always improve the shooting time. For now, it's 0. So you launch 3 artifacts instantly because the actual artifacts is just under the flywheel. But there are still things to improve.
This is super cool, guys. Thank you so much for sharing. You should be really proud of this design.
Thanks.
Wow. You wouldn't think from the back that it would look that quick, but that's really fast.